Am I audible? Am I audible? Hello? Abhay sir? Hello? Hello? Sir, am I audible?
Yes, you are audible. Hi, good morning. Am I audible?
Sir, yes, sir.
Okay.
Good morning, everyone. Sorry for the delay. It's
There
my
seems to be an
pleasure to
echo from your
introduce
side.
Dr. Anjaneya Dixit, currently serving as an assistant professor in the Department of Civil Engineering at the Indian Institute of Technology, Roorkee. Dr. Dixit specializes in structural engineering with a research focus on sustainable construction materials, ultra high performance concrete, cement chemistry, and carbon storage in cementitious systems. He earned his PhD in current civil engineering from National University of Singapore in 2021, following an MTech from IIT Delhi, BTech from IIT Bhubaneswar. Prior to joining IIT Roorkee, he worked as a research fellow at National University of Singapore, and also he has professional experience with Bharat Heavy Electrical Limited. He has received numerous awards, including the prestigious Ramajuna Fellowship and medal from National University of Singapore for excellent PhD, and also a certificate of appreciation from the IIT Roorkee for being among the top 5 young faculty members in undergraduate teaching. His research contribution includes over 22 peer-reviewed journal publications globally. He has also led 5 major research projects funded by DSP, DRDO, NBCC, and Tata Steels, focusing on sustainable construction and advanced material system. We honored to have him with us today. Please join me in welcoming Dr. Anjaneya Dixit. Welcome you, sir.
Thank you so much for that warm introduction. A couple of points. I have not worked with DRDO yet. I didn't get to receive a project from them. Uh, but yes, it's a pleasure to be here and to talk about something that is very close to my heart: sustainability and sustainability in construction materials. I hope that my voice is audible.
Yes, sir. Yes, sir.
The volume is also good. Okay, right. So, should we? Before I start, I just want to thank SRM University, Dr. Roy, for having me here, for giving me this kind invitation to speak on something that uh, not only is part of what I do, but is the need of the hour in terms of how we perceive our future. Uh, we have to understand that not without incorporating sustainability or without incorporating the respect for nature, we will not be able to achieve a livable society in the coming years. So, all the research data that I will be talking about here, all those things aside, because as researchers, we tend to become disconnected with the humane aspect of our research. What's the actual economic, socio-economic impact of whatever we do? So while I would be talking about my research, I would also request the audience to, in the back of their mind, to have that connect with their own surroundings and understand that why it's so important that we need to talk about the same jargons that we keep on repeating: sustainable construction materials, sustainability, low carbon construction, net carbon, things like that. By now, by and large, everywhere we see the same dictations and terminologies being regurgitated again and again. And in doing so, we might be losing the appreciation we have for this idea. Without dwelling much into the philosophy of sustainability, I'll just delve into the research. Uh, Just give me a minute because I'm accessing Zoom through my browser. So I need to figure out some things first. So is my PowerPoint visible? Uh, Dr. Roy, Mr. Holland, can you just respond?
Yes, sir, visual.
Okay, I'll just go into the full screen mode. Please confirm if I'm not in the presenter mode. So you can see the full screen. Should I start then? All right. So good morning again, everyone. So I'm Anjaneya. I'm an assistant professor here in the Department of Civil Engineering. And why are we living when it has always so long? It has been a boon to the humanity. Uh, Knowing that okay, concrete is to blame, why is it that we're not able to do away with concrete completely or come up with an alternative? So what's the thing? What are those things aspects that are limiting us? And with that, what is the way ahead, particularly from the Indian perspective? So I'll be talking about three materials that are in different stages of research or acceptance in the society and what the future entails for them. Before I start, just a quick introduction has been given, but my sustainable materials lab works on novel building materials, usually something that has been valorized from waste. I also work on 3D printed concrete and carbon storing in cementitious composites. So, should you wish to reach out to me, you can find me on LinkedIn or even on my Google website that is shown here. Right. A bit of a background. So, 1824, Joseph Astin, a very primitive kind of innovator, finds something that he terms as Portland cement. And then it took about 70, 80 years for the ordinary Portland cement that we know right now to actually come into the market. But ever since this cement was invented, you can see that the population of the world has somehow matched with the cement production. Now it's a chicken versus egg kind of thing. Which came first? Cement production that had made sure that we had safe housing, we had safe places to work, and therefore the population could rise, or population rose and therefore the to cater to the demand, cement production increased. It's very difficult to justify that, but they went hand in hand in tandem. And with the improved living standard, every continent, every country in its due time started producing cement and in large quantities. The future growth, as per the International Energy Agency, the growth trend for cement production is shown here, where we will be reaching up to 5 million tons of cement every year from our current 4,200 tons, million tons. At the same time, we also know that we are increasing CO2 into the atmosphere, and we are witnessing CO2 levels that have never been witnessed. They are the unprecedented levels, crossing the 400 ppm mark for the first time in history, recorded history. And with this, we have doomsday predictions. We have clocks such as this, which can be seen in the mcc-berlin.net, where there's a timer which says that this is the ultimate amount of CO2 that we can emit to the atmosphere. Once we cross that, there's no going back. We would have destroyed the planet for good. Now, where does cement come into this? If you look at the global cement CO2 related emissions, they have increased according to the production of cement. Now, why is that? For every ton of cement that we produce, we have components coming from limestone decomposition, the fuel that is required to produce cement, the associated ancillary activities like grinding and quarry. The problem is, even if you go completely or do away with all the fossil fuels and start making cement from completely green energy, still you would have about 50% of the emissions coming from limestone. This accounts for about 500 kg of CO2 for every ton of cement that is produced. And that's a big number, considering that we'll be producing about 5,000 million tons of cement every year in the coming future. And this is why the building sector accounts for, now these figures vary from, depending on where you're looking at, varies from about 8 to 11% of the total CO2 emissions. The current CO2 emissions in the world is about 41 or 42 gigatons, and of that, 11% is because we have to create the things that are needed: our roads, our buildings, our dams, our highways, bridges, right? And to create them, another problem is the sand. We are running out of sand. So we are using about 40 billion tons of sand every year globally. Most of it is mined from the river. And so sand mining is therefore becoming a big issue in India because we have started to understand this and curtail the quarry of sand or mining of sand from natural riverbeds. Notwithstanding, we'll see a huge surge in the demand of sand in the coming years because we're going to see a huge surge in the demand for infrastructure. Add to that, we have already depleted almost all of our natural sand. We have started destroying our aquatic and related wildlife, and not through just the carbon emissions, but because of the sand depletion also. We have made concrete one of the most destructive materials on earth. Now, this headline from the Guardian seems a tad dramatic. It may not be the most destructive and per capita, or rather, let's say per kg, but considering that concrete is the second most used material after water globally, when you add up बूंद बूंद से सागर बढ़ता है, ये सागर इतना बड़ा हो गया है that the overall implication of the concrete and what it does to the environment is humongous. So what is it that is limiting us? We know now that if you produce cement, we'll emit a lot of CO2. If we use sand, we'll have to take it from some natural sources, right? Though there are manufactured sands coming to the market now, but they are still not as good as the virgin natural river sand. So what is it that is limiting us? Why are we not able to come up with this alternate solution? We'll start with cement first. Okay, the ordinary Portland cement, which constitutes about 90% of the total CO2 cement that is produced globally, it replicates the most abundant elements on Earth's crust to some extent in its composition. The four elements being silicon, aluminum, calcium, and oxygen. So these are the most commonly occurring elements in the Earth, and they are the same elements that are found in the largest quantity in your OPC. So, in terms of optimizing the composition, elementally, cement OPC has done a very good job in that. Now, why is this important? It's important because all the constituents of OPC come from, or any form of cement come from earth. So, any material that is able to replicate the composition as is means that you will not require a lot of extra material or extra processes other than the bare minimum needed, such as heating, calcination, clinkering, etc. So OPC as such is very optimized. Add to that, you have about 1 century or even more now, almost 1.25 centuries worth of data on how OPC based concretes behave. And now that's very important because we want to construct a lot of our buildings that we want to last for 100 years. The embankments that were created for the rail Chenab, they are supposed, on their own, they are supposed to last for more than 100 years. Now that is possible because we know how the concrete is going to behave in that environment under those loading conditions. Okay, so we can predict what will be the strength that will be left after 100 years. Will it be good enough for the bridge or not? So doing away with OPC with something that does not have a big knowledge base is the challenge. Furthermore, it's not like our population is going to come down very soon. There are predictions that it might peak much earlier than what was early anticipated, but we'll still see about 47% rise by the end of this century. Now, we have seen this in India that rural centers are losing their population and most of them are moving towards the urban centers. And urban centers, by definition, require a lot of concretization. Where is that concretization going to happen come from? From all the sand, gravel, all the rocks that we're using. So their demand is still going to increase because we are still increasing in population. So there's no other way. Now, even if suppose by some uh, magic, some wand, if we were able to arrest the population, okay, this is the population of the earth, full stop. The problem doesn't end there. we still have to maintain the already existing infrastructure. Now, this is some data from 4 years ago, where it was predicted that America would need about $4.5 trillion worth of money just to rehabilitate its existing dams and bridges. And India is yet to reach at that level of infrastructure. So imagine when our turn comes, when our infrastructure matures and starts aging, how much money, how much material we would be needing to just maintain the infrastructure. Add to that the current trend where a lot of new structures, because of poor workmanship or poor oversight or poor quality of material, they are they are falling, they are collapsing way early, way ahead of their anticipated lifetime. So that means that India will have a double challenge. That not only our properly constructed infrastructure is going to age and require intervention, our new infrastructure, because of our poor practices, will also require intervention. So there is no way around concrete. So in light of this, how do we go ahead? Well, the three R's of reduce, recycle, and reduce, of course, they are going to work here also, where you have to try to reduce the amount of material that you want to use, try to reuse as much material as you can, and recycle what was used previously and still is okay or usable for your work. While doing all this, you have to ensure that not only the project cost is under control, because, of course, no good intention will be accepted unless it is economically viable, and that should be the case. We should not be chasing out white elephants at the cost of money. At the same time, you also have to ensure that your embodied carbon is reduced. It should not be like you are trying to reuse or recycle some material, and while you are making it reusable, you are imparting too much energy into it. So much so that it becomes more carbon intensive than the original material that you were trying to replace. In this, you have a plethora of options. Okay, some can act as binders because they have reactive calciums, aluminase, and silicates in them. Some act as fillers because they are majorly, they are inert. So in such a case, how do you choose when you have so many options? Again, you go to the basics. You see that it has to be compatible to the concrete. That's the first and foremost thing. You can't add aluminum waste directly to the concrete. Alumina has a very bad reaction with the alkaline environment of concrete. It reduces hydrogen. It makes concrete porous. It makes it weak as hell. This is why the calcium high aluminate cements, the calcium aluminate cements that were used right after the World War II in World War II devastated Germany, they started deteriorating in a couple of decades itself, because alumina rich cements usually they give you very good early strength, but they will also at the same time deteriorate faster. So it has to be compatible, whatever waste that you use. Okay, it has to be available, and not just geographically. I'm talking about time wise. It should not be that it's a waste that is being generated by an industry that's operating now, but the future of that industry is itself questionable. Maybe 10, 20 years, that entire industry might be obsolete. So you put so much effort and energy into something to discover a new alternate material for concrete production, and then turns out that 20 years later, that material is not, that byproduct, the industry that produces that byproduct is not operational anymore. And I'm not talking about just one factory or one outlet. I'm talking about the entire industry. In this regard, uh, the developed countries, they have started questioning steel slag. Unlike India, they have started to recycle a lot of their steel, and they don't have the demand for steel as high as we have, virgin steel. So for them, steel slag seems to be an option which is going to deplete in the future. Not steel, I'm sorry, the blast furnace slag, which is one of the most common alternate binders we use worldwide after fly ash. Speaking of fly ash, a lot of countries, developed countries, again have started shutting down their fossil fuel plants, coal based. If there are no coal based plants, where do you get the fly ash, right? So it's not about just the geography, but it has to be on the temporal time scale as well. Whatever new material that you want to try out, it has to operate in both of these axes. It has to be available in most part of the country, and it has to be available for a long period of time, at least for the next 30, 40 years, so that you can justify putting so much of money, energy, infrastructure, and resources into understanding how this alternate material can be used as a concrete ingredient. And paisa. Nothing that I am talking about will work if it does not is not fiscally sound. Until your solution is it at least breaks even compared to the available solution, that is either OPC or natural sand, there is no point chasing around with alternatives. So that's the catch here. So these are, I usually use these three parameters to judge which alternate material sounds best. In today's talk, I'll be talking about three of these materials, which are abundantly available throughout the country and are in different stages of acceptance in the society. We start with clay, which is the most common. And I'll tell you a little bit about Singapore and why this idea of clay and one of the materials I wrote was biochar that came into picture. So, to give you a perspective, Singapore is a tiny island nation where I did my PhD from. They dump all their material, all their waste. They burn all their waste, first of all. They collect it and they incinerate all their waste. Okay. And whatever ash that forms out of that incineration, they dump it into an island called Semakau landfill. The photograph is shown here. The patch that you see is filled with water. That is the only remaining land that they have for their landfill ever. This is the last place where they will dump, and after this, either they will start using this ash again, or they will stop consuming, or they'll start recycling even aggressively. So that is the commitment that they have made to themselves. This patch of land is what we have defined. All our waste will go here. The moment we start running out of space, we will start changing our lifestyle completely. We will not be constructing any new landfill. So as a nation, that's applaudable. Now, the problem is they thought that this would last till 2045, but at the current rate, might not even last till 2035. They have two of the biggest challenges for them was with a waste that you could not recycle was the excavation waste that come from all the tunneling works and a lot of wood waste that was generated in their country. So now, excavation waste, of course, they can't dump here, but it has to go somewhere. So it's a big challenge. But because Singapore is very particular about how it dumps its waste, so either it will take money from you as a penalty, or it will ask you to put money so that the waste can reduce in volume, or it can become usable for other purposes. For the second thought, how to make it usable for other purposes. The idea came that you can use the excavation waste, that's basically clay, which has high surface area, and which we know that has minerals such as kaolinite, which if you fire at let's say 600, 700 degrees centigrade, they will restructure themselves so that they become pozzolanic. And when you add it into concrete along with cement, they will produce additional products. Okay. So
Sorry, sir, to disturb you. Your
yes,
slide is not moving.
my slide is not moving. Which slide am I stuck on?
It is challenges to sustainable concrete. Future tense of interest.
Oh,
Page
how?
number 10.
See, oh my God, I'm so sorry, guys. Uh, I'll stop sharing and I'll start sharing again. Let's see if it works.
Okay, sir.
Right. Is it visible now? Can anyone please confirm if it is visible?
Yes, sir, it is visible. Slide
Oh,
number 17.
slide number, have I reached slide number 13? I'm going full screen. Please confirm if the full screen is visible or not.
That's slide number 13.
Visible? Can I go ahead?
Yes, sir. Yes, sir.
All right.
Yes, sir.
Thank you. Please let me know the moment my slide gets stuck. Okay, I don't
Sure,
know how
sir.
that happened. Thank you. So this is what I was talking about, that we recycle, we choose the right kind of material for recycling, okay, based on the compatibility, the availability, and the economics. And based on that, I'll discuss these three materials which are in different stages of acceptance and research. And I was talking about Singapore. So on your screen, you see at the bottom there is a small island, and the photograph shown here. So Singapore is dumping all its burnt waste, the ash here, and it has no further backup plan once it runs out of this island. The half of that island is only the available land for their ashes. So they're aggressively trying to recycle or reuse as much of their material as possible. So what we did in Singapore was we used clay, which if you heat, you will be able to produce a pozzolanic material that can be used as an alternate to cement. And not just that, if you do use it in the right amount, it can not only impart good strength, it can also improve your durability. And in India, you have IS codes for Portland calcined clay pozzolana, as well as a very recent code. I'm sorry, I forgot to mention here, IS 18189, which came a couple of years back. That's on limestone calcined clay cement, LC3. Right. So during my research in Singapore, we have tried a lot of ways through which we try to utilize this excavation waste, majorly as a binder, but we also dabbled with using it in combination with some other binders, making pallets out of it, and coming up with aggregates, lightweight aggregates that could either be used for, just a minute, that could either be used for non-structural applications or even for structural applications. Right. So coming back, in Singapore, we did about 5 types of different types of clays with varying kaolinite content. Now, kaolinite, for those of you who may not be aware of it, kaolinite is a naturally occurring mineral in clays. And
Sorry, sir, to disturb you. Once again,
again,
it is on slide number 13 only. It's not moving, sir.
oh, what I'll do is I'll not go to
Full screen,
the full
powerful.
screen mode. Okay, I'll
Okay,
not go
sir.
into the full screen mode. I'll just stay in this.
Okay, sir.
I think because of the animations, it's not moving around.
Okay, sir. No issue, sir.
Okay,
Okay.
right. So this is again the compatibility, the availability, and economics issue. And the landfill I was talking about in Singapore, where they're dumping all their ash. And this is what I was talking about. So kaolinite is a naturally occurring mineral in clay. What it does is, if you heat that clay, if you heat the kaolinite to 600 or above temperatures, higher temperatures, there is atomic restructuring that occurs at that temperature. And if done right, you are able to obtain uh, a different structure, okay, like this. And this structure is called metakaolin. This metakaolin has reactive aluminates and silicates which can react with the calcium hydroxide that is generated because of cement, when water is added to cement, which is basically a pozzolanic reaction. Even fly ash works the same way. Fly ash plus calcium hydroxide gives you CASH, or calcium aluminate silicate hydrates, which are the binding entity in concrete. So with that idea, we developed binders and fillers out of this excavation waste. We also developed pallets, which were used as lightweight aggregates for structural and non-structural applications. And we studied about 5 different clays, different types of clays with different kaolinite content, and therefore different reactivity, because the more the kaolinite, the higher the reactivity. And we found that in cases, depending on which kind of clay we are using, compared to a normal OPC based concrete or mortar, we were able to get up to 3 times improvement in durability, which was measured using rapid chloride permeation test. Okay, and so much so that we got featured in the local news channel also for our work. Right. In IIT Roorkee, I'm using clay without heating for generating printable mixes, low carbon printable mixes, and we have been able to achieve very good performance based on clay. concrete, because clay can act as a natural viscosity modifier and can help improve two things: extrudability, that is the ability of concrete to come out of the printing nozzle, and buildability, that is the ability of concrete to stack up in layers without collapsing. So clay is something that has very easy acceptance in the construction industry, because even historically, if you see, surkhi is a common word that has been used, and surkhi was a very common ingredient that was added along with lime, because bricks were being manufactured millennia ago, and lime was available readily to them. So they used to add surkhi to lime to solidify their mortars. And this is nothing but a pozzolanic reaction happening. You use lime, which is calcium hydroxide. You use sirki, which is nothing but a burnt clay, which is metakaolin to some extent. You add the two and you have pozzolanic reactions. You have insoluble hydrates, which will not wash away with water. So clay, the understanding around clay, the clay's availability globally, okay, and economic wise also. So if you try to produce, we are still yet to break even. But if you're producing cement using metakaolin, or let's say the cement that I talked about, limestone calcined clay cement (LC3), uh, it's very close to the amount of the cost of normal OPC. So one of the ways that you can see the economics working out in favor of these alternate materials is if you start charging for the carbon credits. So they work very well in developed countries, because developed countries have a very strong model for carbon credit. Any material that does not emit carbon, if it is used to replace a material that emits carbon dioxide, you save money on that. So not only do you break even for the extra cost you are putting in, you might even generate a profit because of those carbon credits. India is yet to have a formal policy around this, but once that policy is implemented to achieve the net zero 2070 target of the government of India, the economics will also start tilting in favor of these new materials. Jumping to a next material. So incineration in India is a very big problem. North Indians, I think you are at the heart of that incineration problem in Sonepat, and you would see that every year for 2 months, and the residual effect of that for the coming remaining 4 months at least. That we have so much of carbonaceous particulates in the air that it has actually become a calamity, and we are not able to find out solutions, large scale solutions, so that the alternative to burning becomes profitable. Now, one of the ways to do this, apart from other techniques, we have started using these rice straws to produce plates or utensils or cutleries or papers and pulps. A big industry can be concrete itself. Now, this second material, the biochar I'm talking about, is very much known in research, but is yet to be translated into industry. So that brings us to a second stage of material. Now, what is biochar and how do you produce this? So, if you burn any wood waste or any organic matter or in the open air in the presence of oxygen, what you're essentially doing is you are letting the carbon in those materials interact with the oxygen, produce carbon dioxide, and go away in the atmosphere. But what if you are able to achieve that or heat that in the absence of air? Okay, in such a case, what will happen is all the fats, all the lignins, all the cellulose, hemicellulose in the wood waste will go away. Okay, what remains is about 70 to 80% of pure carbon. So if you look at your table on the right top, this was another study that we did, raw sawdust, where we had about 44% of carbon dioxide, carbon content, elemental carbon. The moment we pyrolyzed it at 500 degrees centigrade, heated it at 500 degrees centigrade without oxygen, without air, the char that we obtained was more than 70% carbon. So essentially, all this carbon which would have gone to the atmosphere, you have saved and you have kept it inside. The advantage, in addition to all this, is these materials are porous. These are some of the electron microscope images. So you see there's pores in those materials. Now these pores are excellent site to retain water, and if used in concrete, they can act what's called a internal curing agent. A material that holds water in its pores, and when mixed in concrete, when the concrete is gaining strength, it can provide water from the inside also. So that's what's called what advantage you can get from a biochar in this, in addition to storing carbon directly inside that char. But the challenges is the pyrolysis condition, and from where are you getting this uh, material, the source material, the feedstock. Because some organic matters such as peanuts, they are high in phosphorus. Okay, now if you use these materials, you make a char out of it and then you use it in the concrete, you're adding phosphorus into the concrete, which is not good. We try to limit all the alkalis and such kind of materials in limited form when we're using in concrete. The other thing is how stable your char is, because it's an organic matter, and in concrete we have a big no for any organic matter to go in. You have to ensure that the char that you're using is virtually essentially an inert material. To do that, you use what's called an oxygen to carbon molar ratio. You test that, you find out how much oxygen is present in comparison to carbon. The less the oxygen, the better it is, because it's the oxygen that creates those reactive functional groups which might do unwanted reactions. So the less the oxygen carbon ratio, the higher the life of or stable life of char is. So usually we prefer zero point 0.3 or below, which is very easy to obtain through normal pyrolysis itself. Furthermore, the temperature at which you heat the biochar, the speed at which you reach that temperature, these two things control the amount of pores and the way of the type of pores that are generated in the biochar. This is important because if you want to use the biochar for internal curing, you want a specific size of pores to be available, no larger than that, no smaller than that. Smaller pores will not be able to hold water effectively, and larger pores will create voids inside the concrete that instead of providing internal curing, they will act as weak zones. So what has studies or what is the research around this? Well, if you're using in normal concrete, you can go as high as 10% by weight of cement. So suppose if you are using a normal concrete with about 350 kg per meter cube of cement content, you can add 35 kg of biochar in it. And that 35 kg, assuming 70% of carbon content, would be somewhere around 25 kg, approximately 25, 24, 25 kg of pure carbon that you're storing inside the concrete. Multiply that by another 2.2 times to get the carbon dioxide equivalent that you have stored inside your concrete for 1 cubic meter. And not only that, when you're doing so, you are able to increase your strength as shown here, because the internal curing effect of your biochar can help improve the hydration. Even though the biochar itself is weak, the additional hydration products that it generates can improve the strength. Now, a very peculiar case of UHPC. UHPC is ultra high performance concrete. These are very special type of concrete that have strength above 120 megapascal. So my majority of my PhD research was on UHPC, and I used biochar to see if that internal curing effect can be obtained in these concrete also, because for UHPC external curing works very ineffectively. In the first day itself, the density of the UHPC becomes similar to what a 28-day-old normal concrete would be. So in a 28-day normal concrete, if you try to cure externally by putting it in the water tank, it will not work. So the same is the case with UHPC. So we try to cure it internally. But what we found was, yes, there was a very significant increase in the amount of hydration that was taking place. But a bigger find was that we were able to control the shrinkage in UHPC. Again, another problem in UHPC is that you balance or you trade the strength with shrinkage. Very high strength, but also very high shrinkage. So we were able to control that shrinkage by using biochar, because this biochar kept releasing water in different parts of the concrete, and it didn't allow the concrete to shrink as much as it would have without biochar. The same is the case with normal concrete. You can see a large reduction in shrinkage if you're using biochar. And as I've said, you can also see high early strength if you're using biochar, provided you have prepared it correctly from a correct feedstock. So this is about biochar. For now, biochar has not yet found commercial acceptance because the feedstocks that are being used have traditionally they don't have the utility in concrete sector. So organic matters generally stick to one industry, which is organic based. Like I've said, paper pulp or pulp based utensils or cutlery, something like that. So it is yet to come in large scale in the industry. The translation of the research to the field is yet awaited, but the research is there and it is overwhelmingly positive. It does say that you have to fine tune the biochar, but you can get desired properties relatively easily. So that brings to me to the third leg of this talk, the MSW or the Municipal Solid Waste Incineration Ash. Now, in India, we have started to become a little more aware about how we are dealing with our municipal solid waste. Uh, the Ghaziabad landfill is one of the biggest eyesores and a really nightmare for the administration to get rid of. I'm very glad when I learned that the other two landfills near NCR are being taken down, and in due time, I think Ghaziabad landfill will also be taken down and repurposed. But what do they do with the waste that they're taking out? That waste will have to go somewhere. If it is being reused or recycled, very very good. But I don't think a big chunk of it is reusable or recyclable. So why don't we incinerate that? The government of India has taken a lot of initiatives in waste to energy approach. Okay, and what they are essentially doing is you take the waste, segregate it properly, of course, put all the dry waste in one, what you can say, separate out all the dry waste that have good calorific value, and you incinerate that. By doing so, you have two advantages. You are reducing the volume by about 70 to 80%. Okay? More importantly, you are able to generate electricity out of that. When I gave you the example of Singapore, where they are incinerating all their waste and dumping the ash here, they are generating 5 to 8 megawatts of energy, depending on how much the waste they're burning. This through all in just one plant, and they have 3, 4 similar plants. So, though their energy requirements are in thousands of megawatts, but still, if they're able to generate electricity out of just waste management, that's a very good, what you can say, idea. As a matter of fact, one of the waste to energy plants in Bidadi in Bangalore, it generates about 11.5 megawatt of electricity just by burning waste. So, municipal solid waste ash or incinerating municipal solid waste and generating the ash is a good way to manage your waste. The ash that is generated is relatively inert. Mostly 80% of the total ash is bottom ash. 20% is the fly ash that goes through the exhaust. So I'm focusing on the bottom ash for the moment. India's trend, particularly in the major cities where this incineration will actually work. First of all, incineration is not something that can be applied to every municipality. A tier 3, definitely it will not work, it will not be viable. But for a tier 1 or even a tier 1.5, tier 2 cities, okay, they generate 6 to 7,000 tons of waste every day. Out of that, at least 50% is dry waste. So their waste to energy plant works well, but still they become economically unviable because the electricity that they are generating, they sell it 7 to 8 rupees approximately, whereas from solar or from thermal you get it at much lower cost. So to stay competitive, they have to find other avenues of producing money. What can be that avenue? Produce the ash and sell it as a construction material. Of course, treatment work, etc. is needed, but that's one of the financial models that they can try. So when we have been trying out this with in our case, we got ash from, I think, one of the plants in Sonepat itself, and what we found was the bottom ash is very high in silica, alumina, and calcium, but also in phosphorus and alkalis. And that's a big red flag. We don't want these materials in heavy metals, sulfates in our construction material that's eventually going to end up in concrete. So that is a challenge. Also, the research around municipal incinerated ash, MSW ash, is also nascent. It's very variable because the MSW itself is variable. You don't even have to go to different cities to compare. You take just one city and you monitor the waste ash for just 1 month, and you'll see such a big fluctuation that it becomes very difficult to suggest one technique how to make this ash usable for engineering applications. So right now we are trying to do something. We are trying to replace this bottom ash as a sand replacement. But the challenge is that this ash is highly porous. It stores a lot of water when we try to replace natural sand with this ash. And in turn, what it does is it reduces the workability really bad. And essentially, the ash is not as strong as the sand it is being used to replace. So you see a big drop in the compressive strength also. Anyway, this is in the nascent stage, and only time will tell how the uh, research progresses. But if tried, municipal ash presents a big opportunity for us because India generates in one major city we are generating 5 to 8,000 tons of waste, right? So if the waste management, waste segregation becomes very efficient, this idea definitely can take up, and that's the problem here. The segregation right now in India is not as effective, and therefore, what happens is a lot of low calorific value material ends up in these plants. So, a plant which is actually needed to generate electricity might need additional fuel to burn this low calorific value materials. So, instead of plant generating rated at 10 megawatt, might use some extra electricity to burn the materials that are of low calorific value or that are wet in nature, that are not dry. So that's a big challenge right now. But because we have started incinerating hardly a decade ago, so we are still new to this. We'll learn our way, and if we keep trying on, we'll definitely find a way out it. So that's about it. I conclude. I tried to discuss three different materials that are alternates to concrete. Two of them alternate to cement, and one of them alternate to a sand. And in different stages of research and practice, with calcine clays being very well accepted in construction sector, then biochar, good, well established in research, but yet to be taken up in the industry, and then municipal ash, which is uh, no in both the cases, both for the research as well as for construction industry. So with that, I'd like to stop. I thank again SRM University for having me over and giving me the chance to speak on this topic, and I'll be happy to answer any questions if there are. Thank you.
Thank you, sir. Any questions? Any questions? Okay. Thank you, sir.
Are you, if you're using maybe two speakers because of that?
Am I audible now?
Yeah.
Okay, once, thank you, sir.
My pleasure. My pleasure.
Thank you for your time, valuable time out of your busy schedule to share such a valuable and thought-provoking presentation.
Thank you. Thank you.
I'm sure everyone here has taken away something meaningful from today's session. So we
So
also
there's
put
a question: how much biochar is sustainable and market available? Okay, so in India, biochar is yet to take up. We are not producing biochar for the purpose of construction. A lot of biochar, or rather activated carbon, is being produced for filtering purposes. By activated carbon is a big constituent for filters. So traditionally, whenever we produce any kind of char or any kind of carbonaceous material, that is mostly used towards these kinds of materials.
any other question.
And one more thing, Professor, to add on to this is, again, this is just one or two research points. So I'll suggest you to also take what I'm about to say with a not just a pinch of salt, but a handful of it. Uh, if you are able to extract everything out of a biochar as much as you can, so what they say is for every kg of, or rather, let's say 1 ton of feedstock that we pyrolyze, because pyrolysis is an energy intensive process. We are putting in energy, right? So for every ton of biochar wood or feedstock, organic feedstock that we are burning, pyrolyzing, if you are able to extract all the oils that are coming out, if you are able to store all as much carbon inside the char as possible, you end up saving 870 kg of carbon dioxide for 1 ton of feedstock that you pyrolyze. So that's one of the research data points. But unless it's done in field and pilot projects are taken up and then data is generated on field for large scale implementation, only then we'll come to know how much sustainable actually biochar becomes. So I suppose that's about it.
Thank you.
Okay, I'd exit the meeting then.
Thank you, sir. So I request all the participants to turn on the camera for group photo.
Thank you, Professor Kerr, for your kind comment.
Thank you once again. Thank you, everyone.
Okay, so should I leave then?
Yes, sir. Thank you.
Okay, thank you.
Student classes were approved.